So without further ado, let's get started with our first speaker of the afternoon. Please join me in giving Mr. Quoc on stage for his opening talk.
Hello, everybody. 15 years ago, when I was a grad student at Stanford, and we had this question, we had this debate among the grad students at Stanford, and the question was, if you have a powerful AI, what do you want it to do? And actually, many people had a really interesting answer for this question. And, some people say, if you have a powerful AI, I think you could use it to improve our productivity, right? Make our work faster. But actually, that question gave me a lot of thinking, and I realized that if I have a powerful AI, and if let's suppose that the limitation is infinite, right? Then I would say, if I have a powerful AI, I would go to the AI and I would ask, can you invent me a vaccine for all cancers? Or can you invent me a new materials, a better material for solar panels? Or can you give me a solution for the P equal to NP conjecture? So in other words, if I have a powerful AI, I want the AI to solve the unsolved problems for humanities. And that thinking, later that I realized that this is connected to what people found in psychology called system 2 thinking. So there are certain prompts or query or questions that if you ask to people, it trigger what called the slow thinking. People will start thinking really hard and deeply about the question and try to solve, to find solutions for this question. For example, if someone asks you a hard high school math problem, you will spend a lot of time, minutes to like an hour to solve it. So that's called the slow thinking. And in psychology, they call it the system 2 thinking. Now, they call it system 2 thinking because it's trying to contrast against what they call system 1 thinking. And then system 1 thinking is basically if you have some kind of simple question like, how old are you? How many fingers on your hand? If I see a red light, should I stop? This kind of question, you can actually respond immediately. And that's what in psychology, that's called system 1 thinking. So what I was thinking is that if we have a really powerful AI, I would try to trigger the system 2 thinking into solving really hard and very complicated unsolved problems for humanities. And during this journey, around 2014, I realized that in order to solve this very highly complex problem, for example, if you ask the AI to give me a solution to the P equal to NP conjecture in computer science, the response is going to be a long proof of the conjecture. Either you prove it or you disapprove it. Or if you ask it to come up with an answer for, what is invent me a vaccine for all cancers, then it's going to be a long, pages long answer. But at the time, we didn't have the AI that's capable of doing this long form response. So how do we do it? So the way that actually some of my colleagues and I, Ilya Sutskever, now chief scientist at OpenAI, Oriol Vignal, now still my colleagues at Google DeepMind, we found out a clever solution to this problem. So this problem in machine learning, what we call the transduction. So basically, what we do is we have to, in NLP or in most of machine learning, what we need to do is to generate a really long-form response. But in order to generate a long-form response, you need to generate, so our solution is to generate one token at a time in that long-form response. So instead of predicting a long response at a time, you predict one at a time, and condition on the first token, you predict the next token or the next word. And given the next word, you predict another next word. So this simple process of predicting the next token turned out to be really powerful, because once you predict the next token, you can predict your next million of tokens. And hopefully that next millions of tokens will give you the proof of P equal to NP conjecture, or what is the vaccine for all cancers. So that's the vision. Now actually, whatever inventing a vaccine for all cancer is actually, way further than any, technology at the time. So what we said, okay, let's train this model on what we call in an internal data set that people chat to each other. So let's say internal at Google, we have a data set where people will log onto a system and ask the technician to help with their computer problems. So we recorded all the exchanges between people, the users and the technicians. So, and then we trained the model to mimic how to respond. And in around 2015, Oreo and I trained this model. We call it the neuro-conversational model, where you can just log in and ask it. Let's say I type in this example, like I say, the machine will ask me things like, what is the error that you're running into? And then I tell them about my problems, and the machine will suggest me to go to this URL and enter the name and password, and then you will have the information. And then the URL here, we redact because it's an internal URL. But if we click on that URL, it actually gave you the correct website to fix your problem. So in a sense, by mimicking the next word prediction, the machine actually start to learn. And they start to learn about information, about how to respond to certain queries that look like what all the interactions happened in the past. So this is some form of pattern matching, but it's already quite clever. And because of this success, around 2020, we gathered a lot of resources at Google to scale up the training of this chatbot. And you could see this as like a precursor of externally what people call the ChatGPT. So internally, in 2020, we train a model, and as we make it larger, so the x-axis is the perplexity, which is the how well the model is trained, and the y-axis is how well it behaves like a human. And what we saw was that as we make the model larger and train better, the model get better and better at behaving like a human. And the perplexity gets smaller, meaning that the model needs to be bigger and better trained. So around 2020, we saw that if we scale the system up, it will get meaningfully better at mimicking human conversations. And if you keep scaling it up, it will exceed human ability to have a conversation. So this is basically the precursor of what we saw today, a ChatGPT. It's basically scaling up, actually can give you a really good system in chatting. And what we found is in certain cases, if you ask it to do things like write you an email or produce a summary and things like that, it would not do very well. So in 2021, we trained a system called FLAN. And basically, we took a lot of NLP tasks, formalized with some instruction at the beginning. For example, let's summarize this email, or let's summarize this article, or let's translate this sentence. And then we use a system to, we fine-tune the model that train on dialogues of user dialogues. And then the system becomes very good at following instructions. So you can get it to write emails, write code, and produce these very beautiful long-form responses. So this is basically, like an early version that you can call it like an early version of ChatGPT internally at Google. And we basically, in 2021, and then we actually open source this model called Flan T5. And the Flan T5 model is still one of the best models, state-of-the-art model, open source in the world still. But during that process, I still believe that what we have achieved is just system one thinking. In other words, if you go to the model, you ask it to do something, it will take a few seconds to actually accomplish the task. But if you ask it something very complicated, it will not be able to do it. Like if you ask it to solve a hard high school math problem, it still cannot do it. So my passion is the same. I want to make this chatbot to be able to do what I call system two thinking. So how do we do that? So the intuition is the following. So you need to trigger the model in what we call a step-by-step thinking. So in this paper, 2022, in the year of 2022, we developed a method called chain of thought. Now this is a breakthrough in reasoning, and let me try to explain what it's doing. What you do is that what we have is this data set called a high school math problem. For example, here's a high school problem. Roger has 5 tennis balls, and we buy 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And if you say the answer is 11, right? You do your internal math dialogue a little bit, and you give the answer is 11. And then when it comes to another question, you ask the model what's the answer, and the answer is going to be wrong because it doesn't produce the internal dialogue. So what we should do, and in chain of thought, what we should do is you ask the model to write down what it's thinking. So instead of just give you the answer, it will have to give you the step-by-step logic that to get to the answer. So for example, in order to get to the answer of 11, it has to say, Roger started with 5 balls, and 2 cans of 3 tennis balls, each is 6 tennis balls, so 5 plus 6 is 11, so the answer is 11. So you want the model to do this behavior, to generate the step-by-step thinking. And this step-by-step thinking is basically is a beginning of what I call a system two thinking, where you have to get the model to think a little bit longer and more slowly. And it is a breakthrough because for most of the reasoning data set, you started seeing like a huge jump in performance, like from 20 to 30% accuracy improvement. And the reason is that I think if you think deeply about this, is actually because one reason is that it mimics the psychology of humans. Because a lot of the time, when people answer mathematical questions or reasoning questions on the internet, they will start thinking, they will explain the answer first. And then after that, they give the final answer. So that's one way that you can interpret. But the other way that you can interpret this is you allocate more computation at test time. You give the model more room to do the computation. And this is basically what they observe in psychology about slow thinking. And then actually, the chain of thought gave rise to a new idea, which is, let's suppose that if you do a chain of thought, every answer you come back with, for example, you give a new question to the model. Every time you sample from the model an answer, right? For example, for this complicated question, the model could say the answer is 18. If you sample another time, the model can give you an answer of 26. If you sample another time, the model will give you an answer of 18 again. So how do you know which answer is better? And it turns out that the way to find the best answer is to do what we call majority voting. So we sample from the model many, many times, let's say 100 times. And then we look at the final answer, and if the majority of the answer is 18, we say the final answer is 18. And this idea, what we call self-consistency, is another idea on top of chain of thought to allow the model to think even more. So instead of just producing one answer, we producing 100 of answers, and then selecting, the model can select among the answer, the best answer that has the majority. So if you look at all the data set that we have, like for example, the doing arithmetic, common sense, SWAM, and ARC, most of it, if you do this self-consistency technique, you start to see better and better performance, like getting much better compared to the baseline. For example, in this arithmetic data set, you can get from 52% to almost 75%. So much better in doing computation. And this idea of giving the model more ability, more computation at test time is actually a form of what I discussed earlier, called search, right? You use search augmentation with the model to get better performance for reasoning tasks. We recently have this, for on coding, what we do is that we give the LLM the ability to produce many samples, and from the sample we can have unit tests. So in a lot of software engineering queries and prompts, you actually have the unit test to check whether the answer is correct or not. And the unit test is usually easy to generate. For example, if you have a task of sorting numbers, the unit test for sorting numbers is actually quite easy to write. But the code to do sorting is actually very difficult to write. So long as you provide the unit test, what we do is you use a new unit test, ask the model to generate code, and for all the samples, we look for the samples that pass the test. And the sample that passed the test turned out to be the best program that we can use. And using this very simple idea that actually you can just sample many sample from the large language model, check which one that passed the test, and then use that one as the final answer. Turned out to be a very successful recipe for this dataset called the Swebench dataset. So the Swebench dataset is a famous dataset in programming or software engineering. And people use it to benchmark a lot of methods like ChatGPT, Gemini, and Llama, and all the language models. And the state of the art, if you use GPT 4.0, the state of the art is only is down here, right? 20-something%. But if you use this method of repeatedly sample from the model and then pick the samples that pass the unit test, turn out to give you much better performance when you sample to like in the thousands of samples and get you to 54% accuracy. So the idea of actually giving the model more ability to think and search at test time is something that people don't do a lot. For example, if you go to ChatGPT and if you ask for how to fix this code, it will just give you the answer. But this research tells you that if you ask the model, allow the model to sample many times, and then somehow check the correctness of each of the answers on its own, and select the one that it finds to be correct, turns out to be the better method. So you want to give the model at test time 1,000 times more compute than what you want to see it today. And this what I think what gives rise is that nowadays people train models using putting a lot of compute into training the models, but they don't think a lot about test time. How do you decode the model? And what this research is telling you is that you should allocate more compute at inference time. You want the model to be able to select out of 100 of samples, which sample is the best. Now going back to the question of the thought experiment, can we solve an unsolved mathematical problem? Actually, this is one of my lifetime dreams, is to be able to solve using large language model or using the AI to solve the P equal to NP conjecture. And if you think about it, it's actually very difficult because most of the large language models are trained on human data on the internet. And if you ever have a proof for P equal to NP, that's a novel proof. That's something that you've never seen before. So the perplexity or the likelihood of that proof is actually, the likelihood of that proof is very low. So what we want is to allow, the question is how you can allow the AI that we have today to get to the point that it can do something that we never seen before. Now, inspired by this thought experiment, in the last few years, my team have started looking into theorem proving. And one area of theorem proving that we're doing research on is geometry. Because when I was a kid, geometry was my favorite subject. And I've also heard that Vietnam is doing very well in Olympiad when it comes to geometry. Like Asian countries are very good at geometry problems. And in this research, what we found out is that if you train a large language model to predict the next token in geometry, it turns out to be quite inefficient. It doesn't solve a lot of geometry problems. If you copy and paste some of the geometry problems and you send it to ChatGPT, the performance is very low. It actually achieves almost 0%. So the way that we solve this problem is we augment it with a symbolic system. So a symbolic system basically it's like a search method that guide the model to search through the proofs. And basically it generates the sketch of the proof. And then the large language model will fill in some of the key steps in the theorem proving. And using this technique, we went from, our method was able to achieve gold medal level performance in mathematical Olympiad. And recently, just a couple of months ago, AlphaGeometry together with AlphaProof, I'm going to talk about AlphaProof in a minute, but together with, you were using AlphaGeometry and we participated in mathematical Olympiad live. And AlphaGeometry was able to solve the problem within 30 seconds after we formulate the problem in the language of AlphaGeometry. I would not be able to solve this problem. My mathematical ability is not good enough to solve this problem. I think a lot of my colleagues at Google find this problem quite hard. But the model was able to come up with an auxiliary point. So in a lot of geometry problem, the question is basically trying to come up with some auxiliary point. So the red line is what the model was suggesting, a new auxiliary point, which is the point E, which is a novel point. So if you want to come up with all points in this figure, there's many possibilities, right? You can pick, you can pick K and L, and then you connect with the circle that go on around A and B. That's end up with E. But there's another possibility. You can take K and D, right, and then connect with another circle to get another point. So there are many possibilities. But the large language model was able to suggest point E, which is key to find the solution for this problem. I find this amazing in the sense that within 30 seconds, it was able to prove this hard problem. Now, AlphaGeometry participated in the contest with another model called AlphaProof. Now, AlphaProof was a large language model trained on a formalized language called Lean. So when you work on mathematics, most of the mathematics that you write is that you work with is called natural language. But Lean is like programming language for mathematics. So we train this large language model on this formal language. And test time, we allow the model to do what we call test time reinforcement learning. So the model was able to search at test time. So they spent a lot of compute. So in one of the problem for this year IMO, we spent 3 days to compute the final to compute the solution, and so it will do this test time IL and searching, and together in combination with AlphaGeometry, AlphaProof was able to solve 4 out of 6 problems at IMO. So with 4 problems, we achieve around 28 points. So each problem is worth 7 points. So we solved 4 problems. So that means we achieved 28 points. One of them is geometry, and 3 of them are normal math problem like algebra, number theory. So we are this year, in order to get gold medal, we have to get 29 points. So we were 1 point short of gold medal. Just think about that. The AI is already at near gold level in a mathematical Olympiad. In some sense, I think this is already many people don't know how to appreciate this result. But in some sense, I think this is a beginning, what I call a narrow super intelligence in some domain already. Because it's already better than me in proving mathematical, proving mathematical problems. At a side story, I've heard that this year the Vietnamese Olympiad team didn't do very well at the mathematical Olympiad. We achieved we were ranked like 35 or something like that. And one of the reasons, actually I was surprised by this because normally Vietnam is in the top 10. So I met some friends at some soccer match, and they went to me and they say, it's your fault that this year we only achieved 35. I said, what did I do? They said, because you solved geometry problem in January. So the committee, the mathematical the selection committee actually deliberately select problems that is not they select most problems, the hard problems in other areas, not in geometry. So I think Thang is to blame for this incident that we are ranked 35. So to conclude the talk, I just want to say that this talk I discussed the idea of system 2 thinking. The idea is how to trigger the model to do more slow thinking. Or in other words, you want the model to be able to solve very hard, high-level planning, complex problem solving. And my claim is that actually using the next token prediction and using ILHF is possibly not enough to solve very hard problems because some of these problems are novel. For example, think of the proof for P equal to NP conjecture, or how to disprove it. I think the proof of it is going to be low likelihood. So you want to augment the large language model with all the capabilities so that it can search the right proof. And I think what we just observe narrowly in mathematics, I think we already enter in some form of superhuman level intelligence. And this is, I think, to me, this is a really remarkable result. And hopefully, right now it's still very narrow because it's in mathematics. But I think my hope is that we'll be able to transfer this knowledge into other non-mathematics abilities, for example, biology or physics. And if we are able to transfer this ability into something like biology, hopefully one day we could go to the AI and we ask, please give me a vaccine for all cancers. It will be able to. And I think that would be my dream. Thank you.